Hello and welcome to Chapter 5. Today, in this particular video, we're going to deal with distributed loads. Now, we've talked about these before. So let's just take an example like what we looked at before. Take a beam. Now, instead of having a point force that's acting in just one place, we have a load that is distributed over the whole length of that beam. So in this case, you can see the height of it is the same across the whole beam. So it's an even distribution. So when we have a distributed load, W is the symbol for the distributed load function. So in this case, we're dealing with two dimensions. So W is a function of X. It changes as the X dimension changes. In this particular case, it doesn't change, but in general it does. So the units of W is always going to equal weight divided by length. All right, so in our example up here, weight as a function of X is constant. All right, so for this easy symmetrical situation, let's redraw this down here. We can represent this intuitively. We know we can represent this just like with a point load right in the middle. All right, where this force is the distributed load times the length. L equals the length of that beam. Okay, now we talked about that before, and that's, I think you got that. Now, the new part is, what about non-uniform loads? Okay, where W is not constant in the dimension of interest. Now, sometimes, depending on the analysis we do as the weeks move on, we're going to deal with the distributed load. Sometimes we need the equivalent point load. So keep that in mind. It's not always one or the other. So let's look at a beam now that has a non-uniform distributed load. So here's our beam, and I'm just going to hand draw a curve here like that, and we could see that this is not symmetric. Okay, we know that the support on the right is going to be taking up more of the load than the support on the left. We don't know how much. We can estimate that, the equivalent load, this is F equivalent point load, is going to be towards the right past the midline. Its position x bar. And this line represents the distributed weight as the distributed load as a function of x. So, just looking at it, we can get that information, but we don't know exactly where f is or exactly what the value of f is. All right, so one thing to note here, when we do this analysis for the distributed weight, we take positive as downward, because most of our loads are gravity and are usually acting downwards. All right, so we can write the force then, the resultant force. Not where it acts, we don't know that yet, but we can write the resultant force as the integral along the whole length of that beam of the distributed load function. All right, now, if you have W as a function of X, that's great, no problem. If you don't, that means you have to break this up into little rectangles, this sort of thing. I'm going to try to resketch my function here. All right, so we're breaking the force, or that load function, into little rectangles of width dx, where x is the distance from some point A. All right, and so x is the distance of that particular rectangle, that particular area of interest, from some point A. We're taking it from the end of the beam there. All right, so what are we trying to do here? Well, the first thing we're going to do is find the total moment about A. Okay, and you'll see where we're going with this in a minute. Okay, and you get that by summing all those little pieces, typical calculus stuff. You're summing all the little bits of force, each one at their distance from x. So the moment about A is going to equal the load function dx. Okay, so this is right here. This is the differential of force. Okay, this little blue area. Right, that little bit of force. But for the moment, we have to multiply that times the distance at which that's acting from A, which is x. All right, so dF is the amount of force generated. By the blue area above. Okay, and obviously there's, like infinite of these as you go along the beam. Okay, so when you express it, x times, when you express it like this, and you do this over the entire beam, this gives the total moment about A caused by the distributed load. Okay, so this right here we're calling MA, just the moment caused by that little one area, that little bit of force. All right, now, but what we want to know, right? What we're getting back to is if we want to replace this distributed force by a point force. How do we know where to put that equivalent force? All right, so just a reminder here. Here's our situation. Right, we have this. This sort of thing. And we want to know for this F, where is it? What's the location? All right, F, remember, is going to be the integral along the whole length of that distributed load function. Okay, so we have a way we can deal with this now. So because the moment calculated using distributed load must equal the moment calculated using the equivalent force. Okay, that's got to be true. So that means the moment calculated using distributed load, x, w of x dx, must equal the force times a distance, right? With that x bar being the distance at which an equivalent force would act, the distance from that point A. Okay, so just an aside for right now, we're looking at planar solids. So these are, the load is constant in the z direction. Okay, so when we can manipulate this around, and we get that distance is the moment divided by the force, and the moment for the whole thing is the integral from 0 to L of x times the weight function dx, all over the integral from 0 to L of the weight function. All right, so, and keep in mind that this is the area under the distributed load curve. Okay, just adding up that whole area. All right, so now, this is going to be your key relationship. We're going to step through a problem, an easy one. We're going to go back to our original first problem that has a constant load. Right, so here's our beam, here's our constant load. All right, so I'm just going to draw a couple arrows because you know. All right, so this is W equals a constant in units of typically pounds per feet or newtons per meter. But, you know, any variation of force over distance works. All right, so we're going to have two reaction forces. And so I'm going to draw the two situations. So this is the constant load, or the distributed load situation. And now here's the equivalent situation. We still have the same reaction forces. But now we have an equivalent force that's acting at some distance from A, and our goal, assuming we know W, is to find what that distance is. Okay, so how do we go about that? Well, we use our relationship right here. So first thing is the total load, which we're calling F, equals the area under the curve. So F is the integral from 0 to L of the load function. Now, W is a constant, though, for this one. So W comes out of the integral. So it's just 0 to L dx, which is just W times length. So that means x bar, going back to our expression up there, is the integral from 0 to L x W of x dx over integral 0 to L W of x dx. Okay, this is M, this is F, right, because moment is just force times distance. So this one the integral of x w dx over WL, because we got that from up here, and W is constant. Put my limits in here. Over WL. Okay, continue with this. X bar equals x squared over 2 from 0 to L over WL equals L squared over 2. Those W's go away. And this ends up being L over 2, which is what we knew. Okay, that one's no surprise, but it's good to do one that you know so you're confident that the system works. All right, that's it for this. When we come back in the next one, we're going to deal with a problem where that load is not constant.